we're going to look at inverse functions and relations. Relations and functions have inverse relations and functions, or basically it's their opposites of what they look like. To do an inverse relation, remember a relation is a set of ordered pairs. Two relations are inverse relations if and only if one relation contains the element BA, whenever the other relation contains element AB. And so basically what that means is that we're going to switch places with the variables in our problem. We just swap the x and y variables in the equation, or in the case of a table of values, we're going to swap the input and output values. So if I'm looking here at my first example, it says to graph the function that equals 1/2 the absolute value of x plus 3 and its inverse. And its inverse is written as f to the negative 1 of x, and that tells me that I want the inverse of that. On the table on the left side, we have just a table about input and output values for the absolute value function, which we learned that that's probably one of the easiest ways to graph an absolute value function. And then on the right side, it's blank to put in the inverse. And literally all we're going to do is swap the input and the output values. So these are my inputs in my original function, and they're now going to become the outputs in my inverse. So where I have f to the negative 1 x, that's going to be negative 3, negative 2, negative 1, 0, 1, 2, 3. And then where I have the output values, which would be basically my y coordinates, I'm going to put those as the input values for my inverse function. 1.5, 2, 2.5, 3, 2.5, 2, and 1.5. And then I want to graph those ordered pairs. First I'm going to graph just the original function using a set of ordered pairs. And I'm going to graph that in blue. Okay. We'll just graph those. We have negative 3, 1.5, negative 2, 2, negative 1, 2.5, 0, 3, and then it's going to come back down because we know that absolute value functions make a nice little V here for us. And so it should look a little something like this. I'm going to graph the inverse function in red, and we'll see what they look like compared to each other. So again, think of this as the opposite. We have 1.5, negative 3, 2, negative 2, 2.5, negative 1, 3, 0, 2.5, 1, 2, 2, and 1.5, 3. And it's just kind of, it's not the opposite, but it's kind of a 90-degree turn to the right. So that's what the inverses look like on each other. One of the tricks that you can use is to draw in the equation for the line y equals x. And y equals x, I'm just going to draw the dotted line for this. Looks like this. In every instance, it's going to look like this, where the x and y coordinates are the same. And you can see that what happens is the blue function, which is the original function, is reflected across y equals x, and that's how you get the red function, or the inverse. So look at the second page. It says to see if an equation is a function, you can use the vertical line test. The equation is a function if any vertical line drawn through the graph of the equation will only pass through the graph once. And so, actually I have the inverse up here, but graph down below what these functions would look like. So this is my f of x function, just like it is on there. And the vertical line test says, well, if I draw any vertical line through there, through that function, as long as it only passes through one point at any time on the function, on the graph, then it's a function. So I could say that f of x is a function. The same thing with g of x that you have on the right. G of x is a parabola. And we can see that, again, I can draw a bunch of vertical lines through there. I'm only going to ever cross the function one time. So g of x is a function. And that's the vertical line test. Now, without actually graphing the inverse of a function, I can tell whether it's going to be a function as well or not. It says similarly, you can check to see if the inverse of the equation will be a function by using what's called the horizontal line test. And that's exactly what we're going to do. We're going to draw a horizontal line. Using the original equation, if any horizontal line drawn through the graph of the equation will only ever pass through once, then the inverse is a function. So again, still using that original function, we have f of x, and we have one horizontal line drawn, and you can see that it only crosses in one place. And we can draw as many as we want. It will still only ever cross in one spot. So we know that f of x is a function by the vertical line test, and its inverse will also be a function because it passes the horizontal line test. If I'm looking at g of x, we already said g of x is a function because it passes the vertical line test. But when we draw a horizontal line through, we actually see where we would cross it 2 times, which means it's not a function. It can only ever touch it one time. Okay, example 2, it says consider the function x plus 3 squared minus 5, and we want to know, is the inverse of f of x a function? For A, B, find the inverse of f of x. C, we're going to graph both, and it says use a graphing calculator. You can use a handheld graphing calculator, or you can use Desmos. Desmos is probably the easiest one, so if you want to use that, you can. To find A, what we're going to do first actually is go ahead and just graph f of x, and let's take a look and see what it looks like. And by graphing it, we can use the horizontal line test and see if it will pass the horizontal line test. So when I graph f of x equals x plus 3 squared minus 5, it's going to look about like this. So I have a parabola, and you can see that if I drew horizontal lines through this, it would not pass the horizontal line test. So we would say that f of x, f inverse x, is not a function. Then it says find f inverse x. So this is a little bit different than using the table and just swapping the input and output values. We are actually going to trade the x and y in the function. So what I want to do is we're going to let the original function we're going to say y equals x plus 3 squared minus 5, and all we did was replace the f of x with the y. And then I'm going to swap the x and y. So where the y is, I'm going to put an x, and where the x is, I'm going to put a y. And then I want to solve for y. So let's add 5 to both sides. And you get y plus 3 squared equals x plus 5. Then I'm going to take the square root of both sides, and you get y plus 3 equals the square root of x plus 5. And then we're going to subtract 3. And you get y equals the square root of x plus 5 minus 3. Notice that the minus 3 is not under the radical. And so our new y is actually the inverse function. So I'm going to graph our inverse. And we'll take a look at that one. You can kind of see if I draw in that y equals x line, that the red, or excuse me, the blue and the green graphs reflect each other. Now, example 3, this is a little more tedious. It says you can graph a function by using the parent graph of an inverse function. Now, since we're using our graphing calculator, the truth is that you can go right ahead and put that in your calculator and graph it. If you're going to use the parent function, the inverse of the parent, here's what you're going to do. First, we're going to just write the parent function. And we do that by getting rid of anything in the function that's added, subtracted, multiplied, or divided by x and its radical in this case. So the parent function would have been the cube root of x. And then the second thing is we want to find the inverse function. So we take our y equals the cube root of x, and we're going to swap the x and y so that now we have x equals the cube root of y, and then we're going to solve for y. We do that by cubing both sides, and you get y equals x cubed, and that's our inverse function, y equals x cubed. And then we're going to graph